In this video, we are going to talk about two concepts, one called zero divisors and one called units, and we're going to talk about them in the context of Zn. So first of all, we're going to review an old fact about integers that involves multiplication and my favorite number 0. We're going to use that to help us define zero divisors. We are then going to look at the concept of a multiplicative inverse, and then we're going to use that to define what units are. And then finally, we are going to look at zero divisors and units if they exist in Zn. All right, so here are two important facts about multiplication of 0, and we've proven these things. So if a and b are integers, the first fact is that anytime we multiply an integer by 0, we get 0. We proved that one in class. And not everybody proved this one on their homework, but some of you proved that if you multiply two integers together to get 0, then one of them has to be 0. So what this says is multiplying by 0, first of all, gives you 0, and it is the only way that you can multiply two things together to get 0. So what is so special about 0 other than this nice theorem? Well, of course, it is the additive identity of the integers. And one of the things we might ask if we're trying to study this type of result in Zn is let's start with asking if Zn has an additive identity. Well, remember, the elements of Zn are congruence classes, which are sets of integers. So what we're really asking is, if I take the congruence class that contains A, what can I add to it to leave it as the same congruence class that I started off with? So what am I going to put in for that question mark? Well, the reasonable thing to try is 0. I mean, that's our additive identity in the integers. If I look at the congruence class that contains 0, that seems like a good candidate for the additive identity for Zn. Well, we know how to add two congruence classes together. We just take representatives. We're going to use a and 0, or I'm going to use a and 0. And the nice thing about that is we know a plus 0 as integers equals a, so that is exactly the congruence class that contains a, and we can see that bracket 0 is the additive identity in Zn. So another question you might ask is, what happens when we multiply by 0, right? Well, again, we know how multiplication works in Zn. If I take bracket a sub n times bracket 0 sub n, that's the same as the congruence class containing a times 0, but we know a times 0 is equal to 0, so again, that we get 0 just like we did for integers. But now comes a slightly different question. What if I tell you I have two congruence classes, I'm multiplying together to give you 0, does that mean that one of those congruence classes, either bracket A or bracket B, itself has to be 0? Well, let's try some out, right? So we're going to look at Z8, right? So that is all the congruence classes starting with 0 and going up to 7. And I'm going to look at two of those elements. I'm going to multiply them together. I'm going to look at the congruence class that contains 4. And I'm going to take the congruence class that contains 2, and then I'm going to multiply those together. Now, we know how multiplication works in Z8. We take the congruence class that takes 4 times 2, and 4 times 2 is 8, so we get the congruence class with 8. But we also know that 8 is congruent to 0, so that is the same as the congruence class that contains 0. So we just found two congruence classes, the one containing 4 and the one containing 2. We multiplied them together, we got 0. But one thing you might notice is that neither bracket 4 nor bracket 2 gives us 0 by itself. So we were able to take two non-zero congruence classes, multiply them together to get 0. So that is a little bit different from how the integers work. So here's a definition that comes out of that. So if I have a congruence class in Zn, we call that congruence class a zero divisor if a couple things happen. First of all, it has to be non-zero. Second of all, we have to be able to multiply it by some non-zero congruence class, call it bracket B, such that bracket A times bracket B is equal to 0. So that tells us something about how zero divisors work. Now I want to start talking about inverses. We're going to eventually get to multiplicative inverses, but I just want to talk about what inverses are in general. So you have seen lots of different types of inverses in your various experiences, both in this class and in other classes as well. We've looked at inverse functions even back in Math 210, and actually, to be honest, a little bit before that as well. So if you have a function, its inverse is, well, we call it f inverse. We've talked about the additive inverse. If you have a number a, then its additive inverse is negative a. We have multiplicative inverses, and that is, well, we're heading towards that. So the question then is, what is an inverse? Well, every type of inverse begins with a binary operation. Without a binary operation, inverse doesn't make any sense, right? So when we're talking about additive inverses, we're talking about the operation of addition. When we're talking the inverse functions, that's going to be based on composition of functions. When we eventually talk about multiplicative inverses, that's going to be based on multiplication. So each of these operations has to have some kind of identity, right? And what I mean by identity is identity with respect to the operation, which means that that's an element that when we do that operation with that element and any other element in the set, it leaves it unchanged. So for instance, our additive identity is 0, additive identity, because when we add 0 to any number, it leaves it alone. A plus 0 equals A, no matter what number A is. So once we have an identity, the inverse of an element under that operation sort of cancels out the element. And what do we mean by canceling out? Well, it means we use the operation to bring the element back to whatever the identity was. So let's see how this works with additive inverse. I know you know what an additive inverse is, but I want to go through this process so you can see how it works with other types of inverses as well. So if you take a number, an integer a, the operation we're talking about with additive inverse is, of course, addition. Our identity, our additive identity is, well, we want some number when we add it to another number, it leaves it alone. So a plus z equals a. And of course, the only integer that does that is 0. So that's our additive identity. If we're talking about inverse, we want an integer b such that when we start with our given integer a, adding b to it takes us back to 0. And of course, that's just negative a. So the additive inverse of a is negative a because two things. First of all, 0 is the additive identity. And when we add a and negative a, we get the additive identity 0. So let's go through this exact same process for multiplication. So we're going to let a be some kind of integer. The operation we're talking about is multiplication. And since we're talking about multiplication, the first thing we have to worry about is the identity under multiplication. So we want some integer z such that whenever we multiply z times an integer a, it just leaves it as a. And of course, that number is z equals 1. For the inverse, well, let's see. We found our multiplicative identity. We want to be an integer b where when we multiply it, because it's a multiplicative identity, multiply it by a, we get 1. And, well, not all integers are going to have multiplicative inverses. In fact, not many will, if we're strictly speaking about integers, right? If we have 8 equals 0, if we try to multiply it by some b, we're always going to get 0, which means we're never going to get 1. So 0 can't have a multiplicative inverse. Even numbers that we're used to having a multiplicative inverse, if I take 2, it's like, what do I have to multiply by 2 to get 1? Well, you got to multiply by 1/2. And that's fine if we're talking about rational numbers or real numbers or even complex numbers, but not if we're talking about integers, right? There's no 1/2 in the integers. So that means that 2 does not have a multiplicative inverse in the integers. And in fact, almost nothing has a multiplicative inverse in the integers. There are actually only 2, just 1 and -1, right? If I want to get to 1 through multiplication from 1, I get 1 times 1 equals 1. If I want to get to 1 through multiplication from -1, I have to do -1 times -1 to get 1. All right. So let's see how this behaves in Zn, see if it behaves any differently, right? So let's take a congruence class, the congruence class containing A. For our multiplicative identity, right, we know that bracket A times bracket 1 is equal to the congruence class containing A times 1. I know what A times 1 is, that's just A. So bracket 1 is the multiplicative identity. It leaves everybody alone. So that is the congruence class containing the multiplicative identity in the integers, containing 1. And so, I mean, if we're going through the same processes we went through for integers, it's pretty easy to see that the congruence class containing 1 and the congruence class containing -1 both have multiplicative inverses. I'm going to ignore those because they're too easy. I'm going to see if I can find any interesting multiplicative inverses, ones that we would not expect. All right, oh, any others? Yeah, that's what I said. So I'm going to look in Z11, and I'm just going to look at the congruence class containing 3. Now, if I'm just looking at that, you might be thinking, you can't have a multiplicative inverse of bracket 3. You'd have to have like some kind of 1/3 or something like that. Well, remember, all we're really looking for is some congruence class to multiply by that to get 1, right? So I'm going to multiply the congruence class containing 3 to the congruence class containing 4 and see what I get. What's the worst that could happen, right? Well, I know what 3 times 4 is. 3 times 4 is 12. So we get 12 in Z11. However, one thing about 12 is if we're thinking about congruence, 12 is congruent to 1 mod 11. So that's actually equal to the congruence class that contains 1, which is our multiplicative identity. So that tells us that the congruence class containing 3 has a multiplicative inverse. That multiplicative inverse is actually the congruence class containing 4. And if you want to be technical about it, the congruence class containing 4 has a multiplicative inverse as well. It's the one that contains 3. So once we get to the definition of a ring, right? So for our 2 examples right now are the integers and Zn. An element of that ring is called a unit if it has a multiplicative inverse. All right, so now I think you're ready to work on the activities on the PDF file called 0 divisors and units in Zn, and that file is included with this video.